All right, looks like we got a small crowd today, so we'll go ahead and start. Welcome to the RTOP for October. As usual, we're still working on the Owens Valley March Western Conference. I'm also looking for any more observation reports for the journal. That's due by the 12th. And if you can send those in, that'd be great. And let's see. Okay, now we're getting people in. All right. Okay. Jason, let's go with you first. You got anything going on?
Yes, actually, Andrew and I have completed our mapping of the LEO triplet. Now that the 20-meter scope account is back up to having enough credits for us to use. So I'm going to go ahead and share my screen here. Let's see. Let's do entire screen. Okay. Share. Come on. All right. And then I'm going to go ahead and open this. And let's do this. Okay, can everybody see that? Yes. All right, I'm going to put this down here. All right. Oh, am I on? Yeah,
we're good. Yeah.
Okay. So these are some of the same initial slides that we had in our previous mapping talk, just to catch anybody else up who hasn't seen the previous ones. But the 20-meter scope is part of University of North Carolina, Chapel Hill Skynet program. It's the only radio telescope on that. All the others are opticals. And SARA members can have access to that for free. So it's something that's covered by our dues, and it's open to anybody anywhere in the world. So it's a great asset that we can all make use of. For our mapping exercise, we used the high resolution setting. We set our center frequency at 1420.4 megahertz, and we used on-off mode with 10 seconds on, 10 seconds off, and we did 10 repetitions. That's actually considerably more time than we used for a lot of the other galaxies, but the LEO triplet is getting to distances and power levels that are low enough that we need some dwell time to get enough signal to really see a clear spectrum. But again, we're using off target as our calibration, and then I pull in the data from the file that gets generated into an Excel template that I've made specifically to do this analysis. And what we do is we'll do a linear fit on the background, the regions of the spectrum that don't contain the actual spectrum we're looking for, and try to flatten the area on either side of the actual spectrum that we're looking at, and then normalize that to 0. And then we can do analysis on peak brightness and peak Doppler velocity. And so we create both velocity mappings and amplitude mappings using some of the conditional formatting tools in Excel. So this was our mapping plan for the LEO triplet. The 3 cells that actually have the names of the 3 galaxies of interest were points that we did, earlier, before we did this mapping exercise. We did a spectrum for each galaxy separately, and then as I threw them onto a grid, those were the 3 points in the grid that were already colored in. And then we looking at some professional surveys, we could see significant features of this group of galaxies that we wanted to try to see if we could capture. And so that kind of led to our mapping plan of how far off of the center of those galaxies we wanted to look. This is the raw end results of our peak amplitude and peak velocity mapping for this grouping. And you can see here we have our brightest point is NGC 3628, and then our other 2 brightest points are the M66 and M65. But you can definitely see there's some other structure here that's clearly visible in the amplitude mapping. So I've overlaid the hydrogen mapping done in a professional mapping that was done at the VLA in the early 2000s, and also then one that was done, I believe, also in that same time frame, slightly earlier with Arecibo, and it has slightly lower spatial resolution, but still shows the major features. So you can definitely see this long plume here is clearly showing up in our mapping, which is pretty exciting. And then here's our velocity map. And if you look at the velocity map from the professional survey, the velocities generally line up quite closely with what the professional data is saying. So, and then here is our references for this activity. The paper that we used for our overlays is referenced here. This was published in 2022, but the observations were done in the early 2000s to 2010s era. And then the rest of the resources cited here are just more information generally about the Skynet and the 20-meter scope for people who are interested in learning more about that. So, and then here is Andrew Thornett and my contact info if anybody's interested in reaching out to us for more information or comments or questions. So anyway, that's all I got for today. So I'll stop sharing. Well, I'll leave it sharing for now, just in case anybody has any questions or go backs. So,
Any questions? Well, as usual, excellent work. This is really good. And all right. Well, let's go to Andrew while we're so promptly named into that report.
Oh, okay. Gosh, we're being very quickly getting things. Yeah, it's been wonderful fun doing this stuff with Jason. Not least of all because he knows his stuff, so I sit there and enjoy the ride to a great extent. But I'm very grateful that he takes me along for it as well, which is amazing. It's nice to be able to say to all the people locally that my remote telescope is 20 meters in size and located at Greenbank. So Yahoo butts to you if you're saying about your 100-odd millimeter thing that's in Spain. But anyway, it's just great stuff. But the other thing perhaps I would like to talk about, I'll just show here, I'll just share my screen, is GNU radio, which is what I'm sort of getting a little bit interested in recently, and what I do when it's raining and windy outside. So I don't know how many of you use GNU radio, but it's this it's this thing called GNU Radio Companion, and essentially you have a load of blocks which are bits of code which are pre-programmed, and you can actually, if you know what you're doing, write other bits of code to go with it. And you can see on this screen here, I hope you can all see my screen, can you? It's just showing a flow chart, I hope. So this is an example of a GNU radio companion flow chart, and essentially you can shove these sort of blocks, just sort of drop in sort of plug and play type things, just drop them in. What you see is what you get. Link them all up, and you press the button, the arrow at the top in the middle, and it will turn it into a set of Python code, which will then run. So you can actually basically write Python without needing to know how to write Python. That's the general idea. Well, I was spending last Thursday 3 hours with a chap called David Hardwick from the British Astronomical Association, and we were trying to work out how to get this block to work, the one that I've just let's just move this up a bit. Hang on. I can't seem to get to move around. Oh, well. So so here, this STR Play RSP Duo block, which was getting under Windows, but almost everything that you find that uses GNU radio, such as the Dispura set of software that they put out, and they've also got a disk image for going on a pen drive or a Raspberry Pi. But all that's set up under Ubuntu, and I was trying to get it under Windows. I don't know why I particularly wanted to get it under Windows, other than the fact I had a Windows machine, I suppose. But once you've got them working on the SDR Play, which requires a considerable amount of dependencies to be set up, you can then choose exactly which of the SDR Play devices you wish to use, and then if you click on it, you can sort of set things like the sample rate and whether, in this case, it's a duo, so it's got 2 tuners coming in, so single tuner or dual tuner for the same clock. So there's an opportunity here, which thing I'm interested in, to try and do interferometry with it. That's the idea, and then you can do things like change the gain and AGC, etc. And then you, if you know what you're doing, which I don't really do, so I'm just trying to work it out, you can then start doing things like putting it together and FFT blocks, etc., and move over to the right-hand side. Eventually, you can start to these things called these vector syncs and data loggers, opportunities to actually save the data or put it on the screen in as a sort of graph. I don't know if it's actually going to work at the moment because I haven't got a device plugged in. We'll have to see. No, it's not. It hasn't found the device, but basically this would generate a graph which would come up. Now, what stands out about this particular flow chart that I've got here is it mentions 2 RSP duos here, which I have, and there's an opportunity on these devices to take. You can either use one device with its 2 inputs, which would give you 2.5. I think it's 2.5 kilohertz. I think it is of bandwidth, or alternatively, you can take a line out of the one onto the other, and actually use the clock on one to clock the other one, and actually then have the full 10 kilohertz bandwidth on both devices, which allows you to have quite an impressive interferometer going on. And when on the actual blocks on here, you actually duplicate the blocks to actually show on each line that comes out. So really just saying that's where I'm at the moment. And under the auspices of the British Astronomical Association, we've set up another monthly group, which is a GNU radio group for anybody that's interested to get together and try and help each other to be able to work out how to use this stuff, and then how to actually create some perhaps GNC flowcharts that we can share with each other and actually develop software within it. So that's where I'm at.
All right, any questions for Andrew? Now, Andrew, when you get, we've got code that we use at the DSCS on the 60-foot dish for pulsars. And
right.
We basically bring it in, a single channel into that whole system, and it produces a .fill file, which we can then use the pulsar data for. So when you're ready for that and you can track for pulsars, let us know. We can maybe get that running, and you can maybe get a pulsar.
No, thank you very much. That'd be great. I mean, it's surprising how many people are interested in the group. If anything, it's likely to be more successful than the Hydrogen Line group. And the sort of feedback people are saying is that they're really interested in using it, but they find that the learning curve is very steep. So that's, I think, the whole idea of the group is to help each other to try and get past that steep learning curve. So if there's anybody else that's interested who hasn't had an invite for the group but would like to have one, then please let me know, and I can send a personal invite out to you. And I think I also did put a general invite out on the SARA forum as well.
Okay, great. All right, any other questions? All right, thanks, Andrew.
Yeah,
let's go to Robert. Robert Lucas.
Good morning, everybody. Nothing really new to report. I've started, analyzing all the scans I've taken for the last couple of months, but nothing really new to report. Just it just seems very, very busy. And since the government shut down, I've decided to postpone my trip to California for a couple of weeks. So that's basically it for me.
Okay, thanks. Dmitri.
Hello, thanks, Rich. Hello, all. I I I continue experiments with 43 gigahertz telescope. Uh, so there is some news.
What? Oh, there he goes.
2 weeks ago, I told about first test of 43 gigahertz telescope. Some tracking here, observing of moon eclipse in the beginning of September, and attempts to observe Canis Majoris silicium oxide line 43 gigahertz seems not too successful because line uh, is well fit to expected velocity and shape and line is but very high level of line up to 200,000 Yansky. This is too much. RFI is suspected. It can be radio relay lines in 21, 22 gigahertz second harmonics interferences. This week, new attempts of new observations a bit higher than previous attempt. So any RRLs is was down, and RFI interferences from radio relay lines is expected lower. This is telescope in observations were very low elevation for these frequencies, about 8 degrees, and high atmosphere losses for these elevations. New results is new results here. About same velocities, expected velocities. You can see a line that can correspond to Canis Majoris silicium oxide line, but also a line present here that was not expected, and I think that RFI is still present in the spectrum. The line is enhanced on 4.5 dB of atmosphere losses. This line is not enhanced. I think this is RFI. So I do not exclude RFI fully in 100%, but it can be observations of real Canis Majoris silicium oxide line. The star was quiet in the time of previous observation in the mid of September. So the first observation, I think it was RFI. It was RFI with high probability. For 43 gigahertz is all for now. I also have news for observations of infrared supergiants in L bands in Skynet dish, but I think this is next time. If some questions, I will be glad.
Andrew, you had a question about what he's using to plot this?
Please again.
Andrew, you had a question?
Oh, sorry, I put it in the chat. Yeah, I was just wondering what that software was that you were using to display your data.
Software. This is software written by me. In the beginning of coding was 2080s. 2080s already 6 years of continuous development of the software. Software for receiver. Receiver USRP ETOS Research USRP B200 Mini and separate program for post processing of received data. So you can see screenshot from post processing utility of this packet of programs.
Okay, thank you.
All right, good stuff. Thanks.
Thank you.
All right, let's see what we got here. Eduard, the new YouTube channel star.
Hello, can you hear me?
Yes.
Great. Okay. So yeah, I've been quite busy. So I got a few things to share, if you don't mind. And this one. Share. Then I want to put it in presenter mode. Yes. Okay. So yeah, I've been quite busy doing some continuum observations and some other stuff. So yeah, recent activities since the Drake launch 2 weeks ago. I've done some routine observations of Westerhout 49 again at 22.2 gigahertz. So this is a long-term observing project looking for massive variability in this source. And yeah, at the moment, not that much is going on. No big changes of flares. So not much to report on that front. So what I did is that I assembled my 3-meter dish again last weekend because we have some reasonably stable weather, or we had some reasonably stable weather until this weekend. This weekend we got a little bit of a storm going on, but yeah, luckily I was able to pack up the feed and secure the dish against wind gusts. So everything is still fine, and next week I can just continue with my observing programs. So what I did during the assembly of the dish is that I shot a bunch of video, and I released a video on my channel on assembling the 3-meter dish. This is following a video that I uploaded about 4 weeks ago on doing kind of a sort of a tour of the dish, showing all the components and doing some demos of the hydrogen line and that kind of stuff. And yeah, it was actually quite successful. At least the first video was on the tour and demo of the dish. I mean, yeah, it got around 400 views, which is, I mean, in terms of YouTube terms, it's like very small viewing numbers, but I think it's still a very great start. And also, I posted it to the posted the link to this video to the Sarah list, and it's got more views on YouTube than probably than there are people who stumbled across this via the Sarah list. So it means that it has some reach beyond Sarah, and that's really great. That means that we are reaching other people as well outside Sarah. So yeah, I plan to do some more of these short videos and some clips of radio astronomy in the future, see where we get. I mean, I'm really not expecting to build a huge audience, but even if a couple hundred people are watching these videos, I'd be pretty happy actually. So, and I consider it a success, just given how much of a niche subject radio astronomy really is. Anyway, so enough about that. So my first thing that I wanted to do actually for this observing project with the 3-meter dish is attempt to detect animal signi again. So this is an OH maser at 1612 megahertz. I have detected it in the past, but that was doing manual tracking. So essentially just pointing the dish at the source and then having to adjust the right ascension and declination every 10 or 15 minutes to keep the source within the 5-degree wide beam of the dish. So you can imagine if you're trying to do like multiple hours of integration time, this is kind of annoying because you have to go outside every 10 or 15 minutes and adjust the altitude and azimuth of the dish. So I thought, well, let's do it different this time and try to do only drift scans, because if I do 3 or 4 drift scans, I get also about 1.5 to 2 hours of integration time accumulated, and I don't really have to do anything for it except starting and ending the recording for 3 or 4 days. Unfortunately, that did not work out as well as I hoped, so I may have got some of the animal signi maser, but it was very weak and buried in the noise. And later on, I also tested at the sun, and I got only about 8 dB of cold sky to sun noise. Whereas if I do the same on just back at 1400 megahertz, I get almost 13 dB. So yeah, I think the sensitivity of my feed is just really poor at 1612 megahertz, because it's now kind of optimized for 1400 to 1420 megahertz. So yeah, I'd first have to do some adjustments on the feed before I can go back to the OH masers. So in the meantime, I decided to do something else and just do some continuum drift scans at 1400 megahertz of Cassiopeia A, because I've never actually observed this source before. So yeah, just as a quick reminder of what my system is like. So I have this 3-meter dish. It's a modular dish. It's not permanently set up in the backyard, but it rather consists of 4 segments around the central hub. And usually all those parts are just stored in a shed. So I don't have to worry too much about the weather. And then when I have a couple of weeks of relatively stable weather, I assemble it and do a bunch of drift scans. So yeah, here you can see also a block diagram of what the receiver chain is like. Anyway, I've gone over this in the past, so I don't really want to waste too much time on it today. But if there are any questions, just ask at the end. So yeah, what I've done for my recording is just like what I do usually. I just set the dish on the declination of the source, and then I just let the source drift to the beam. And in the meantime, I start the recording with the IF average plugin, so that saves a spectrum every minute. And then later on, I can process those spectra. So normally I would do this for spectral observations, but it also works for continuum. So ideally, of course, yeah, there's not really a reason to record spectra for continuum because there's not much spectral information. It's just broadband noise. So ideally, you would just measure total power. But there are a couple of reasons why I still would like to record spectra. So one of them is that I can easily see if there are RFI spikes, and you can see this at the end here on this waterfall plot. So at the very top, so the very end of the observing session of the recording in the early morning, you can see that some RFIs start to pick up. And the other reason is that I'm also interested in the radio recombination line that's at 1399.4 megahertz. And this is the H167 alpha line. So this is a radio recombination line of hydrogen. I've previously detected it in the Cygnus X region. But yeah, I'm interested to see if I can see it in other parts of the galaxy as well, other star-forming regions. But we'll see. That's a sort of secondary goal. Anyway, you can see here in this waterfall plot that there is a sort of a bright band right where the arrow is. So that should be our Cassiopeia A supernova remnant. So yeah, what I then did is that I just averaged all the spectral channels of these spectra, and I plotted yeah, just the average total power against time. And yeah, you can see also here this slight hump. It's a little bit later than what you would expect. But I think the pointing of the dish is just probably a little bit off. Another note on the right ascension axis here, you can see that it's yeah, it counts up even from 24 hours. So it's actually normally it should like you should stop at 24. So again 0 hours right ascension, and then would go to 1-2 hours, and so forth. But yeah, in this case, it's a bit annoying for plotting because then you would like have this a break like over here, and then it would start at 0 again. And I wanted to have a nice continuous plot, so I left it this way. Anyway, so yeah, you can also see there's a quite a lot of like background drifting. So it seems to be that the total power is increasing throughout the night. And what I think is going on here is that this is just an effect of yeah, everything in the surroundings cooling down overnight. And yeah, if your LNAs cool down and the SDR cools down, then the gain increases slightly. So you get a slight increase over the course of the night in the total power. So of course it's pretty simple to yeah, correct for this slow drifting. Just fit the trend line and subtract it. So this is what you get then. So we can see our peak from Cassiopeia A more clearly here, but you can also see that there's also quite a bit of noise in the background. So you can see the total power jumping up and down quite a bit. So I think there's still some low level RFI in here. So next night was a lot more stable and a lot better. So you can see less noise here, except for at the very end, you can see this jumping up and down again. So there was some RFI early in the morning. Usually it's pretty quiet at my location between 10 p.m. and 6 a.m. And then for the entire daytime and most of the evening, you get a lot of RFI. So yeah, this was pretty good. And then the next day again, it's also pretty good, even better. So even less noise overnight. Only again at the very end of the night and early morning, you get some RFI. So what's interesting here is that if you compare these two last traces from the last 2 days when conditions were pretty stable, you can see that there's actually more to see than just the large peak of Cassiopeia A. So what I've done here is that I shifted the right ascension axis so that the peak of Cassiopeia A is where it should be, because well, I'm now pretty convinced that I'm actually seeing Cass A anyway. I mean, we have seen this peak three nights in a row. And now we can start to see that there's also other features in there. So of course there's the initial decline at the start, but that's just the result of the SDR warming up a little bit and then equilibrating with the temperature of the surroundings and the heat sink. But after that, so after about right ascension 20, it gets interesting. So we have a slight bump at a right ascension of 2140. And there's another broad hump at 340. So yeah, 27 in my kind of messed up right ascension scale. So yeah, I was wondering what this could be, and yeah, the first peak, it could be the galactic plane, but on the other hand, the galactic plane is quite broad, as you can see in this radio map from the Dwingelo telescope here on top. So I think it could also be another radio source. It's IC 1396. So this is an H2 region, star forming region, and also is a broadband radio source. So it's not as bright as Cassiopeia A, but it's quite extended. So maybe I'm picking up some of that. And then at 340, there's also a few other of these bright nebulae. So these are Westerhout 3, Westerhout 4, and Westerhout 5, if I remember correctly. So these correspond to the optical Messier nebulae IC 1805 and IC 1848. So they are a little bit higher declination, so plus 61 instead of plus 58, but with a beam of 5.5 degree, half power beam width. They would still like be sort of like within the edge of the northern edge of the beam. So yeah, it's very hard to say for sure what we are actually seeing here, but I think it's just some combination. These two humps are just some combination of the galactic plane, just the galactic plane background emission, and these radio sources. So anyway, this was just an interesting side project, sort of like. It was interesting to see that besides like the big sources like Cygnus A and Cassiopeia A, it's apparently also possible if you have good stable conditions and not too much interference to also see other radio sources or other features as well in the continuum. So anyway, that was it. Are there any questions?
What is your integration time?
1 minute. So it's I'm just continuously recording spectra, 1 minute integration time each.
Okay, thanks.
Eduard, yeah, we saw your YouTube channel and your video. It was really great to see how you store your dish and how you put it together. Your video quality is also very good too. Are you doing like your camera on like a tripod, or how are you filming that?
Yeah, so exactly, that's exactly what I do. I just put my iPhone on the tripod and
yeah, it works well anyway. We enjoy it.
Yeah.
I just want to say that.
All right. Thanks, Edward. Great job. Let's see. Pablo.
Hey guys, what's up? I'm working on right now. I'm working on a 2.1 meter dish, which I have on a truck axle, and I want to add the LNA from the Discovery dish, and I am 3D printing a mount for the MELE quieter computer, which I've set up for that. So I'm building an array. I'm going to end up with about 4 dishes on my property, 2.1 meters on a truck axle, and a linear. I have linear rotors for the azimuth, and that works really well. So basically, I'm going to have positioning dishes, but not tracking. And the time tunnel. Thanks for the memory. Yes, it's my favorite show. I wish I could go back in time. So I'm doing that, and I'm also working on artificial intelligence, validating artificial intelligence for radio telescope use. If anything, any questions that I have about radio astronomy, including calculations, it's answering quite accurately. So I find it extremely useful as a learning device. But still, as far as graphing, which does very well, it's still not validated whether it's scientifically correct or not. But I'm sure it will. So that's basically what I have. It's going to be my 21st antenna on my property. It looks like the U.S. Embassy in Iraq right now, because I have all kinds of antennas. Luckily, I've been here longer than any of my neighbors, so they can't say anything about it. So nothing to show at this point. The Discovery dish is doing a fantastic job, extremely sensitive. So I'm waiting for them to come up with a rotor that they're working on. I think it's going to be like $200. And when I do that, then it's going to be a tracking system. But basically, I'm building an array, and I just want to add all the data and see if I can correlate the data and well, increase the SNR so that I can detect a pulsar eventually through it. So that's all I have to say right now about that.
Okay, any questions for Pablo? And Pablo, I've been using the AI assist on Windows 11 for the same thing, and it's given me excellent answers. So far, so good.
Yeah, it's nothing more than a tool. I mean, I still know how to use a slide rule. I was very good at it, but now I use computers. And this is the next level. It's extremely useful for everything, and especially radio astronomy. I mean, it's answering all the questions that I've had, and I don't have you guys sitting right next to me answering those questions. And it does that. It does it in a way that I, as a layperson, can understand and actually learn from it, as opposed to having a PhD like Rich explaining something and me going like, yeah, I don't understand anything he's saying, but I better nod. But it allows me to actually learn all the intricacies of radio astronomy, make calculations and everything else. So it's extremely useful, among other uses, which I use constantly now, but it's beyond the scope of this meeting anyway. So that's all I have. That's all I have to say about that.
All right. Thanks, Pablo.
Pablo, I had a question for Pablo. Pablo, which SDR are you using for your receivers?
RTL SDR, but I'm thinking about getting the AirSpy because of the, and that's one of the things that I learned from AI, because of the bandwidth, which is wider bandwidth. And it actually, AI recommended that to be able to detect my first pulsar using a 2.1 meter antenna. It recommended that SDR. But right now I'm using RTL. I have a bunch of RTL SDRs, versions 3, 4. I have the NULX. I have a couple of NULX. So they seem to be working great. But the LNA from the Discovery dish, which is a little pricey, but it's all set up with about 25 feet of cable, and it works great. That one's extremely sensitive, so I bought an extra one, and I'm going to actually install it in the 2.1 meter dish at the focal point, see what kind of results I get.
Have you compared the LNA from from the discovery with the, I guess the traditional one that most people use, the Sawbird?
Only visually, not scientifically, and it seems to be more sensitive. It could be that it's well matched to the 70 centimeter antenna that they make. So my next, I haven't quantified something that I can report scientifically, but I will eventually do that.
Great. Thank you. Thank you.
Thank you.
All right. Thanks, Pablo. Dr. Shoshone, I'm sorry, from Zambia, part of our new Drake's Lounge Africa team. Gift, you on? Hi.
Hello, how are you? I'm not yet a doctor, I'm still in Ecuador, but I'm currently in Germany, where I have come for a research visit at the TLS Chaos Satellite Observatory in Rottenburg. So, yeah, so basically, we have been working on some radio interferometric data reduction for a galaxy cluster A1340. The data was observed using the Giant Meter Radio Telescope in India. So I'm here to help out with that bit.
Okay.
Yeah.
Thanks.
So thank you very much for allowing us to join you.
Yeah. It's going to be fun getting the rest of the continent involved too.
Yes.
All right. Thank you. Let's go to Adrian.
Yeah. Don't really have anything to report. So just listening in today.
Okay, thanks. Dan. Yeah. Dan, you're on mute.
I'm very new. I'm basically listening in today and just trying to gather more knowledge.
Have you put up an antenna? You were a ham? Where you're located?
I'm located in Mesa, Arizona. I'm part of the Radio Astronomy Special Interest Group with the Tucson Astronomy Association. I'm a visual astronomer. I haven't done anything yet insofar as building a system. So I'm just gathering the knowledge and just trying to gather more information and knowledge.
All right, great. Glad to have you.
Thank you very much.
Okay, Al Ernst.
Okay, I think I'm coming through.
Yep.
All right. I'm going to switch over to my share, see what happens. Okay, so I don't know if this is coming through. There should be a dish there.
Looks good.
Okay, so my project right now is a 12-foot dish. I have not completed it, but it's getting there. So what you see here is some scaffolding. This was from a football team that didn't need it anymore. And so I took it and built it into a mount for the radio telescope. So it's coming together. I have the struts installed and the rim wire on, and I need to put in some braces here to make this a bit stronger. But that's my project right now. And the reason where I came from on this was a few years ago I tried picking up the hydrogen line, which I was able to do with a 16 element Quaggy, and then eventually I actually could pick it up with a pipan and a dipole, so it was pretty strong. So I was very encouraged to continue on with it, and I built an 8-foot dish last year, and this is the next evolution on it. So I've been doing some some of the hydrogen line stuff, and also measuring some signal in the Lockman hole and mapping that out. But I hope to do a little more refined work now that I will have a larger dish. But it's going to probably take another month before I get this thing up and running. So that's what I'm up to.
Any questions for Al?
Hey Al, this is Jason. So what are you using for your reflector material on this?
That was a big question, and I think what I'm probably gonna ultimately settle on is just some simple wire screening from the hardware store. And you know, I thought of a lot of other ones. You know, there are some screens that you can buy, but they're so expensive that you know, I'd wind up spending $600 or $700 for those, and I'm not sure it's really quite worth it. You know, if we'll see what happens. I know there's a lot more wind loading with wire screening, you know, window screening, but we'll see what happens. Last year, the screening was on the 8-foot dish was kind of problematical because it did accumulate snow, and when the snow gets on there and the wind blows, then it's like a solid dish. So you know, I can tilt it over during the snowstorms so that it doesn't accumulate there, and that's what I started doing. I don't know, have you used any materials like aluminum mesh or screening?
Yeah, I actually used window screening prior on my umbrella type design before I settled on Faraday fabric, and because of the fact that I was folding it up and it tended not to get kinked as much, and so the surface quality was a little better. But Faraday fabric is even more problematic with wind, and so now that I'm located in New Mexico and we have higher winds out here, my next dish design is going to go back to the aluminum window screening as well, because it should be a little more permeable to the wind than the Faraday fabric.
Yeah, I think it would be. You know, I have some of that, and it does work pretty well, but I wouldn't want to put it up there on the dish.
Yeah,
not permanently.
Yeah, definitely not for something that's going to be permanently exposed to the elements. In the case of in the case of my design that I'm working on now, it'll be similar to Eduard's in that it'll be designed to be assembled and disassembled and stored when not in use, so that it's not exposed to, you know, extreme weather conditions at least.
Right.
But you know, there's a trade-off there, because then it's kind of the, you know, the pain in the butt factor whenever you have to assemble it and disassemble it.
Yes, that's true. Well, I want to keep this up pretty permanently, and the school I used to teach at has some kids interested in astronomy, and they requested some radio astronomy work. So we'll see where that goes. I hope they don't lose their interest.
If I can add something here, because I asked that question of AI and came up with 4 solutions for you. I can post them if you want to. The option A, aluminum window screen. Option B, galvanized steel hardware cloth with all the details. I'm not going to read the details here. Option C, aluminum coated fiberglass fabric. And option D, perforated aluminum sheet with all the plus or minuses. I'm gonna post it on the chat for you. But it's saying you only need to maintain a plus or minus 1 centimeter precision across the dish surface, which is very forgiving for hydrogen line, which is I suspect that you want to do.
Now, what about the radio waves passing through a galvanized steel? You know, because it's not as conductive a material.
It says here, galvanized steel hardware cloth, material welded wire mesh, 1/2 inch to 1/4 spacing, reflectivity very good, holes 6 millimeters. At pros, inexpensive, rigid. Cons, heavier and prone to rust unless painted or galvanized deeply. Wind, still relatively open, but heavier frame required. So these are all the things that you can actually ask AI, and it'll give you, with the formulas, what you need.
Okay. Well, then maybe I'll consider the hardware cloth because that's readily available.
Summary: for your 12-foot hydrogen line dish, reflective material, aluminum window screen, plus or minus less than 2 millimeter mesh, surface tolerance, plus or minus 1 centimeter across the dish, wind handling, mesh type for airflow, expected gain 33 to 35 dBi at 1.42 gigahertz, weight about 15 kilograms added for the entire surface.
Okay, and what does it give for the galvanized mesh?
I got to ask it. You want me to?
Okay. Yeah. Could you?
Yeah, if you want me to share the screen.
Okay. I'll de-share.
Because this is where AI shines. And I can send you this. I can have it create a PDF, and I can email it to you.
Okay, stop sharing.
All right. What screen is this? Is that the screen here? Can you see this here?
Yes, I do.
Okay, so I asked that question. I said, this is all I asked. I have a 12-foot dish that needs reflective material. What do you recommend for hydrogen line that's light and wind resistant? It says, excellent. You're working with a 12-foot, 3.565 centimeter meter dish for 21 centimeters. That's an impressive instrument, large enough for real sensitivity, blah, 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 blah. Let's design your reflected surface step by step. And goes into the formula, wavelength, conclusion. You only need to maintain 1 centimeter precision across the dish surface. That's very forgiving. Recommended reflective surface materials because you want lightweight and wind resistance. Will avoid heavy solid sheets. The ideal materials are metal meshes with openings smaller than
1/10 wave.
Well, wave divided by 10 or 2 centimeters. Option A, aluminum window screen, fine mesh material, aluminum insect screen or hardware cloth, 1 to 2 millimeter wire spacing, reflectivity excellent at 1.4 gigahertz, advantages very light, easy to form and attach, corrosion resistant, mounting stretch over ribs, tack or rivet with backing wire or zip ties, which is actually what I do with one of my, I use UV resistant zip ties. Wind resistance, air permeable. Anyway, you can read all of this. Can you read all of this?
Yes, I'm going to screenshot it.
No, I'll send it to you. Just give me, send me, put your email in the, I'll create a PDF for you.
Okay, where do you want to put an email?
On the chat here. Just give me an email. Oh, send me an email to Pablo TWA, PABLOTWA, number 1 at gmail.com.
Pablo, you can also attach a file to the chat if you want.
Yeah, I can do that. Yeah.
I had one other question for you, Al.
Yes.
How are you attaching your window screening to the ribs?
Last year, when I had the 8-foot dish, I just simply used little pieces of wire, stuck them through the along the ribs, and twisted it, and that seemed to work pretty well. And I could control the shape of the how well it complied with the shape of the parabola.
Yeah. That's one of the advantages of using plywood as my structural members. I mean, I had to weatherproof them, obviously, but I could basically just use upholstery staples to attach.
Okay. Yeah.
And it would work well.
Yeah, I would be. I guess I could use plywood here, but I'm in New Jersey, where it's pretty wet. For most of the year, so things can get kind of messed up in the weather, even with weatherproofing.
All right, I'll make a file and I'll put it on the chat for you.
Okay, thank you,
It's making a
Pablo.
diagram, but basically it gives you 4 choices, and you can keep asking and having diagram and stuff like that. Hey, what if I do this and that? What do you recommend? So
All right.
that's how useful this is.
Okay, sounds great. Thank you.
Okay. Thanks, Al.
Can I make a comment on the dish surface thing? When
Go ahead,
we were
Jason.
testing scope in the box thing, I found a really useful test instrument that's ultra crude to put behind a dish, and that's a fluorescent light. You get one of the little compact fluorescent light bulbs, and put it in a work light. The only thing is, if the work light has a metal shell, that'll shield it at 1420. Make sure it has a plastic shell, but put it behind the dish, and you'll actually see your signal level go up if you're going through the dish. And that mesh dish with scope in the box would actually let quite a bit through. Every other dish material I've tried didn't let any. But anyway, remember the fluorescent light is a good RF generator from 1 to 10 gigahertz area, and very cheap and available and very uncalibrated. End of comment.
Yeah, hey Bruce, I wonder if the reason why the scope in the box one lets so much through is because it's linearly polarized, so it's not reflecting very well in the cross polarized direction.
I suspect is what's happening is that when you get to a dish, although the things are perfectly straight across, as you get towards the edges of the dish, you actually have to, should have the stuff twist slightly to match the polarization that goes along with the, odd angle you're making to the feed and the dish surface and all that. So I have a suspicion that that's less than optimal, and also the spacing between those bars at 1420 is apparently letting enough through from crude experimental evidence. It's obvious stuff gets through, and things like screen wire and hardware cloth don't seem to let any noticeable thing through.
Yeah, one thing I thought of when Pablo was when you were showing the that as long as you're smaller than a tenth of a wavelength, you're pretty well good. If you want to take it a step further than that, you could. I've done searches on my own and found this stuff, but it might be interesting to ask the AI about it. There's actually a theoretical plot of RMS surface area versus wavelength that shows you the theoretical efficiency of the dish, as you get smaller and smaller defects. And it kind of shows you, okay, where's the 90% point? Where's the 80% point?
Why don't you write the question on the chat, and I'll feed it through the Star Trek computer, see what she says.
Yeah, I'll put it in the I'll put
whatever
the
question you can. You don't have to spell correctly or anything else, or be just the basic thought, and then I'll feed it through Mr. Spock.
Okay, so the Star Wars fans don't have better computers. Is that what you're trying to tell me? Okay. We'll keep going. Charles Osborne.
Let's see. Not too much to report. I did have a computer failure. I jinxed myself by thinking it was great that I had the computer up and running for 9 months continuously without rebooting or having any crashes. So naturally it shorted out the next day. So I had to replace the Dell. I had a 7010, replaced it with a 7050, similar model, and I was able to switch the hard drives. But anyway, back up and running, 3.7 meter dish with the Sawbird and New Elect Lana post LNA, and then the RTL SDR version 3. So I got all that going again. Just recently. Let's see. Oh, it was good to see the RSP Duo mentioned in Andrew's presentation there. I've got one of those, and I hadn't seen as many software compatibility type things that would work with it instead of the normal RSP play like on the Radio Joe stuff. So anyway, that's about it. Still, I'm back up observing now on hydrogen line again. Don't have anything to show though.
Okay, thanks. Thanks, Charles.
Okay.
Let's go to, what am I looking at here? Preston.
Good afternoon. It's afternoon here. I have nothing to report today. Thank you.
Okay, thanks. Carl Spielman. Carl Jan. Okay. Tom, how you doing?
I'm doing about as well as can be expected and just listening in and nothing else to report.
Okay, we're all rooting for you. Thanks. Let's see. Ed Harfman.
Just listening in.
Okay. Bruce, you got anything else?
Yeah, I do have some comments on what I'm working on right now. I've gotten ordering a bunch from different manufacturers via DigiKey and Mauser. I've got a whole bunch of Zener diodes, and I'm trying to characterize how they behave as noise sources. And so anyway, I'm working on that. Should have something to publish on that, but I'm hoping to find some way we can get a noise source for calibration purposes. It's halfway decent that can be made out of something you can actually buy without having to buy 10 diodes at $150 a piece or something from one of the regular noise diode makers. But anyway, about the only thing I've seem to have positively gotten this through from looking at a bunch of the Zener diodes is the cathode of the Zener diode is always the terminal where the heat goes out. So you want that terminal to be to a chunk of metal so the temperature doesn't change from current flowing through it. But that's about the only thing I've established positively so far. But anyway, I am trudging forward, and we'll hopefully produce something interesting. And learning a lot about Zener diodes and avalanche diodes, and they're really very different. And if you get a in quote Zener diode of above about 6 or 7 volts, it's really an avalanche diode, not a Zener, and very different mechanism. But anyway, so I'm doing a little hair pulling out and trying to learn a little on that. So hopefully I'll have something to publish soon. And that's about it from here. Go ahead, Rich.
Okay. Any questions for Bruce? All right. So I'm last but not least, I've got something updates on my array here. Okay, everybody see that? Okay, so I'm calling this the Meridian phased array because it's basically I'm aiming at the Meridian, and I'm going to be able to steer my phased array in the elevation axis. So far, the learning curve on this is amazing. I've got 2 dishes, 2 LNAs each, and the LNAs are all separated by 3 dB attenuator. By the way, that was recommended by my AI program. So right now, I just gotten all that working last night, and I've got one day of data. I'll show you that in a second. I haven't put the phase system in yet. I've just got the cables combined with a simple combiner right into my RTL SDR. So physically, my 2 antennas are facing straight up at 90 degrees, but the preliminary results show that I'm actually steered 110 degrees electrically. And I'll show you how I saw that. So some lessons learned. The Microsoft Copilot AI seems to be giving very good answers, just like Pablo's more expensive ChatGPT 5, I think it is. I have no idea if they're comparable or not. So, but one thing it did do is that gave me the correct Arduino coding for the phase shift system I've got. Basically, I bought these phase shift modules, and I was going to control them with Arduino, and I just asked it, hey, give me the code for that, and it did, and it worked. So that saved me a lot of time. Also asked for the, I'd heard once that if you put two LNAs in series, you need to put some kind of a attenuator in between, and it recommended that. So I actually had a couple attenuators. So I stuck those in between, and it seems to be working good. The other thing I've done is I was having some significant problems with my 3-meter dish with getting RFI. And so I bought these ferrites, and I stuck them on every cable I could find, any power cable, any RF cable, anything. And it seems to be helping, but that's more of a feeling as opposed to data. So I'll see if that helps though. But I would start recommending, if you guys get ferrites, that might help you out if you got a lot of RFI issues. Last but not least, the Amazon, I was trying to work on, because of my RFI stuff I was getting on my 3-meter dish. I thought I could get this 1400 megahertz bandpass filler from Amazon. And it was, as soon as I stuck it on, it basically shut down everything. There's no input coming in at all. I got a nano VNA and tested it, and it basically was really at 1300 megahertz. And it totally shut off. I mean, the bandpass was actually shut off the 1420 megahertz altogether. So be careful buying that bandpass filler from Amazon, is the bottom line on that. Okay, so what did I get? Right now I've got two dishes, and I'll show you those in the background. And with Ezra, you've got to sort of put in where you think you're at. So this is my 90-degree elevation. You see that little light line? The light line right here is what it puts in for 90 degrees elevation. And what you see is that basically the high slope is over here, and over here. So what that means is that I'm really not pointing. I should have it here. I'm really not pointing where I'm thinking I'm pointing. If you look at the next slide, what it does is it gives the high points in Ezra, and it appears that I'm actually not pointing on my 90-degree up. I'm really pointing up here at 60 degrees, because right now I'm at about 40, but it looks like I'm really pointing at 60. And you can tell from the big area over here that you'd usually get a very long extended signal, which is sort of what this looks like here. That's very preliminary right now, and so I'm going to go take a couple more days of data, and if I can get the data to match here, that shows in my preliminary design I've got some kind of unequal, even though everything's the same right now, I've got some sort of unequal phasing going on in my base system, which is good, because I think I can use this approach to calibrate, and then when I put the phase system on, I can maybe put a automatic calibration in that accounts for any bias or current phase problem I've got in the system. So that's what I've got right now. It's very preliminary, but if this works, that means I can get, right now I'm phasing north 20 degrees from where I think I am. And if that happens again tonight, then I think I now have a calibration method. And then I'm going to go get put the phasing system in and start seeing if I can calibrate out the bias there. A couple of things this is the phase system that I've got, or the digital phaser. And I'm saying the AI program gave me with an Arduino Meg exactly how to wire it up and to the code to call. I'll have to enter the phase shift I want, and it'll automatically program it in. So that was saved me a lot of time. This is the new elec. I got this because it said it was 1.4 gigahertz center frequency. So the problem I did have is I got a nano VNA and I started to use the SWR approach to test it. So I got two of these, and one worked very well with about a 1.9 SWR. The other one came out with 22 SWR, and so I forget exactly. It was Alex recommended taking it apart and looking at it. And in fact, it was the cable was actually unhooked from the antenna. It had broken off the solder. So I soldered that back on. And it came back, 1.3 SWR. So I recommend if you buy any of these antennas, don't just plug it in, because you may have a bad antenna, and unless you have some way to test the SWR, you're probably just running with a bad antenna. Because there's not a lot. There's just solder on the top of these things. So be very careful if you're going to buy your own system to somehow test it, make sure it's a good antenna. This is the LNAs that I've been using, partly because it has the battery in it and it's outdoors. But I did find that this the battery does run out after about 5 hours. So I actually put a power source out there with a USB cable. And so now I've got them all powered with USB. But a nice little thing. These are the 3 dB attenuators I stuck in between of those LNAs. The other thing I had is I originally bought the wrong cable. The cable I bought was not good at the frequencies at 1.4 gigahertz. So I ended up buying this cable. So that's just another thought on cable. And this is the Amazon Ferrite package I got. Had a ton of ferrites in it. I think it's well worth putting ferrites on everything. Anyway, so that's what I got. And trying to get back to the original. Okay. And I've got one person just joined, Dr. Spielman. Are you on?
I believe the audio is working now. Does that sound?
It works. Yep.
Okay, we're getting the video to get started. I usually change that to Carl Spielman, but this is just my second time I've signed on. I had gotten interested for my science class. I teach high school chemistry and physics, and applied for one of the grants to get a scope in the box, which we've gotten most of the parts. I think we're still waiting for I think the filter. It was back ordered. So it's exciting. It's one of the projects I want to do this year with the class, and just excited about it. Great group of people. Lots of really interesting topics. So thanks for letting me join in.
Not a problem. And if your class wants to join in later, let me know.
Oh, great. Yeah, that'd be actually pretty cool to set that up. I will.
All right.
Thanks again.
All right. Nice having you, Carl.
Thank you.
All right. Anybody that I miss?
Rich, before you move on, you've not given us a chance to ask any questions about your own little bit of presentation.
Oh, go ahead.
Yeah, so I'd like to ask, at the beginning, you said something about 2 LNAs with an attenuator. Do you mean you've got 2 LNAs in series with an attenuator between them?
Right. Right. Those things are 20 dB LNAs. And I found that I needed more gain. So you just can't put 2 LNAs in series together, because one will overdrive the other one. They recommend having a attenuator in between. I mean, you don't want to take out. In fact, one of the problems I had is I had I just had some 14 dB attenuators, so I stuck that in between. But basically, it's just destroyed the signal between So I found the 3 dB ones, and that seems to be working fine right now. But if you don't, if you put them back to back, they're gonna saturate the second LNA.
And where are you putting these low noise amplifiers?
Well, on the dish that I showed, it has a little cable, and then I put it right on the LNAs right there.
Right. So each dish has a pair of LNAs, low noise amplifiers, one after the other.
Right, with a 3 dB attenuator in between the LNAs.
And are you using a filter there as well?
No, just straight LNAs. It goes right. Basically, they're going right into from the cable, about a 35-foot cable, into the RTL SDR directly.
Why did you opt to use just two LNAs like that rather than something like a Sawbird?
Well, the original problem was that I didn't want to use the bias T to power the LNAs, and I found with the 3-meter dish, I've got the same setup with the LNAs on my 3-meter dish. When I got a antenna there, I've got two in series with a 3 dB attenuator in between. Works great with no filter.
Yeah, and I know that Ted and I have previously discussed how important filters are, or not, or maybe not, given that the software does such a good job of filtering things. And I don't know whether you or anybody else on this call have got any views on that, whether these days sort of hardware filters are really that useful, given that the software does such a good job of filtering it out afterwards.
Well, my problem, and I've been sitting there experimenting, and by the way, Pablo, I asked AI to give me a formula and a design for a bandpass filter exactly, 6 plus or minus 600 to 1420, 405, and it did. And I've been trying to reproduce that and make myself a bandpass filter. But all the bandpass filters that I've currently seen are not, I can't trust them. And with my Nano VNA actually checking them out and looking at exactly what they look like, the off-the-shelf ones are not. We got too tight of a band right now to take an off-the-shelf bandpass filter.
Since you're not using the bias T, are you using a DC block between the SDR and the LNAs, and in between the LNAs also?
No, actually, these battery-powered ones, they can run by themselves without any DC source, but they have a time limit. So, but they do have a USB input. So basically, I ran an extension cord out there and now have a USB source out there, and I plug them in, and I've got them up on USB all the time.
No, what I'm saying is a DC block, because sometimes it can actually bleed through. Some of the bias T may bleed through into the LNAs and do a number on you. So you may want to, between the SDR and the LNAs, put a DC block in between.
Oh, I see, but I don't have.
They're like $5.
I don't have a bias. I'm not using the bias.
Yeah, you're
T.
not activating it, but sometimes it bleeds through even if you're not activating, depending on which SDR you're using. So as a preventive measure, you may want to put a DC block.
That's an idea. I'll put that on my wish list.
Yeah, they're not expensive at all.
Well, one other thing I noticed, we had all this people were talking about putting a Peltier cooler on the SDR. What I found is that my RTL SDR is running a lot cooler without that bias T turned on. That is a thought if you guys want to put, because I know the Newelec Sawbird has a way to go ahead and put a USB port, USB power into it. My recommendation is run power out to the SDR instead of running it, because the RTL will run a lot cooler.
Yeah, what I found though is that the issue with thermal stuff on the SDR is not so much heat, internally generated heat. It's more temperature stability that becomes the Achilles heel, because you're, especially if you're doing drift scans where you're trying to, spend a lot of time on source over a long period of time. And you're looking for really small signals, stability becomes your problem.
Okay.
And so those of us that have bonded our SDRs to a giant heat sink, it's not to deal with thermal, like actual heat generation, it's to stabilize the temperature so that it doesn't drift around as much.
That's a good point. Yeah.
And the other thing I would mention too is with respect to bandpass filtering, what the bandpass filter really does for you is rejects out of band interference, and so it would become more. I think it would be more important in higher RFI environments, but also I believe your SNR will be affected if you have a good bandpass filter in that signal chain at the front end. You're going to have a quieter pass band with less out of band interference. And what the way that would show up in your performance would be your dynamic range would be less if you were letting out of band energy into your receiver. But at the levels we're working with, I mean, especially doing Milky Way, the signal's high enough that it's probably not that big of a deal unless you're in a very noisy RFI environment. But my recommendation would be to you talked about designing a bandpass filter that had a certain bandpass, a narrow bandpass. I would widen that bandpass, because what you're wanting to do is just grossly limit well out of band stuff. And then so I would widen it up, make it like 50 megs or something wide, because what you're really trying to do is reject stuff that's way out of the band, right? That's where you're getting the benefit.
I don't know that, because if you look at my signal, I mean, theoretically, I'm only, the Ezra is limiting me to certain amount of signal, and it's still showing a lot of RFI within a supposedly protected band.
Mm-hmm.
And I don't know how the RFIs, those spikes you're getting in there. And so, besides, I wanted to play with my nano VNA and learn how to build filters.
Yeah.
So that's probably my real ambition.
Well, and the other thing is a lot of times in the use case, you want to have access to all of the passband in your IF chain. So if you narrow it too much, you're kind of limiting yourself on what you can do with the receiver chain too.
I know that, but that's the beauty of it is that I can knock down. I can if I make my own passband filter, I can change whatever I want. And
that's true.
And that's why I'm trying to learn how to make one. Even though the high frequencies tends you have to learn how to do SMA, connectors and all that kind of stuff.
Yeah.
I do have another question on ferrites. It appears that when I put all the ferrites on both sides of the cable, on the antenna side and the RTL side, that I am getting it a little smoother, but there's no quantitative way I've figured that out. It's just, you guys had any experience in that?
Comment on ferrites. I spent a lot of my career cursing RFI stuff, FCC 15 testing. So I had a lot of cursing ferrites, and the ferrites that you get from Amazon are probably almost as good as a filter you got from Amazon. You don't know what they are. And a ferrite has to be adjusted to the band that it works on. And most ferrites just find surplus of unknown sort. Usually they're good from about 40 megahertz to about 500 megahertz where they have any significant rejection, because that's the area that, at least in the past, computers inside instruments put out most of their noise there. So you needed the rejection there. And a lot of ferrites are no better than a piece of ceramic from a coffee cup by the time you get to 1420. So you need to get a ferrite that's actually rated for that. And I think if you look like in DigiKey, Laird is a company that makes ferrites, and they make ferrites in 3 different bands, and their higher band looks like it'll have some rejection at 1420. The other 2 flavors of ferrite are absolutely useless at 1420. So you get them from Amazon. Who knows what you got, but they were probably not optimized for 1420 is my guess there. And I'll go ahead and probably chattering too much here. So bye.
Well, that's okay, Bruce. It's good stuff. All right, I'm going to have to go look at the. I'm going to have to get my AI to go figure out what kind of ferret and where to buy it. So, ferrite.
Yeah,
Ferrite.
Rich, have you had a chance to measure the actual gain with your VNA of your 2 series LNAs with the attenuator in between them? Have you had a chance to check the overall gain of both of those together?
No, actually, I did I did do LNA by itself, and it was about 20 dB gain. I just stuck that stuff on last night, so I did not actually try to do the combined one. I have a little interpretation of destroying my VNA by overpowering by plugging in and overpowering it. So I wasn't when I didn't want to put too many LNAs in to test with the VNA. But
I see. Okay. Yeah, I think usually you wind up having to put an attenuator in front of the VNA when you're doing the overall gain of those LNAs anyway, and so you just then add the subtracted attenuator from the overall measurement, and so you protect your VNA that way, but you still can measure the overall gain of the 2 LNAs combined.
Yeah, I'm a newbie on the VNA, so I'll probably get there, but I haven't tried that one part yet. But you're right, that's how you do it. And I'm this nano VNA, I really love it, and I think that everybody should have something like this. They're about $50 to a 1.5 gigahertz version. So okay, anybody I miss? Excellent work, guys, and see you guys at Drake's Lounge in 2 weeks. All right, send me your observation reports. I need more journal articles. All right, thanks.